In this lesson on ionic and covalent bonding and naming compounds, for many of these fill in the blanks, you're going to actually go to the ionic bonding tutorial slides or the covalent bonding tutorial slides on our online website. And you will be looking for, see how it says 5 here? That corresponds to the slide number on the actual tutorial. So head over to our course homepage, okay, then go to the Contents tab, and you'll find this here. You're going to click on the chemistry unit. You can scroll down and you'll see interactive animations and video links. Click that. You're going to go and use the ionic bonding and the covalent bonding and the chemical bonding as well. Let's jump into the chemical bonding first so you get an idea of what's going on. So chemical bonds that join atoms together to form molecules and compounds are a result of attractive forces between the atoms. This is our main idea of what I want you to understand today. The 3 common types are ionic, covalent, and metallic, resulting from the shift of valence electrons, which remember are the outermost electrons in the atom. In an ionic bond, you transfer them. In a covalent bond, you share them. In a metallic bond, the electrons are shared not between a couple of atoms, but between many atoms. The attractive forces, such as those between oppositely charged atoms or between negatively charged electrons and positively charged nuclei, bond the atoms together. And you're going to see that. This is our main idea today that I want you to see. For this particular animation, this third one though, the main thing I want you to see is the metallic bonding and get the idea of how metals share electrons. This is going to explain for us why metals are so good at conducting electricity. So here in this particular example, we've got ourselves a copper atom, we've got ourselves a zinc atom, and they've tried to show 2 in the first shell, 8 in the second. Because these are transition metals, copper and zinc, they don't have a max of 8 in their third shell. They have a max of up to 18 in their third shell. So let's just quickly count them and see. 2, 4, 6, 8, 10, 12, 14, 16, 18. So you see this one is classically filled up to its max of 18. That's why you only see 1 in the very outside shell. Same thing with the zinc over here. It's got 2. Then it has the 8 in the second shell. And then 2, 4, 6, 8, 10, 12, 14, 16, 18 in its third shell. So it's got a max there. Again, these are transition metals. They do not follow our normal rule of 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Because they're in between. They're the skip a few. And here we see that zinc has 2 in the outside. So if I had to show that this was an ion, you see there's only 1 electron to steal, so that means copper would have a charge of a 1+ as an ion. And then zinc would have a charge of 2+ as an ion if you were to steal those electrons. So when I put copper and zinc together, you saw this in the other video the other day, you're going to form your brass. Copper is a little bit of a soft metal, that's why you can bend wires. And then that zinc is going to strengthen the copper when we form the brass. The other day we actually saw tin being added to copper, and that gave us bronze. But this is a slightly different version of an alloy. So what's going to keep these little atoms together is the question, because if I was to make them an ion, copper would become positively charged and zinc would become positively charged. So we would expect then that we would actually have them repel each other because they'd be the same. So clearly that's not what's going on. We're not trying to make them ions. Nobody's stealing anybody's electrons. So what's going to hold these atoms together? Well, in these particular ones, the atoms of metals such as copper and zinc have few electrons in the outer shells, as we've seen. Got 1 here and 2 there. And so what ends up happening is you actually form something called an electron cloud. All these little extra electrons are going to end up being shared between all of the atoms in the metal. So it says here, this cloud moves as a unit. In other words, if a few electrons move, they all move. So in other words, if these 2 electrons suddenly decide to go in this direction, that'll push these 2 to there, push them to there, push them all the way around. So they'll be with the new electron coming in, old electrons will be popped out and they'll move and satisfy whoever just became positive. And that's going to hold these guys together really tightly in what we call the metallic bond. It's the sharing of electron between many, many atoms. Okay, so here's the visual for that. This electron cloud, which is negatively charged, pulls on the atoms which are positively charged. Each electron has a negative charge. Each atom has a positive charge because its outermost electrons are free to roam. The pull between the electron cloud and the atom binds the atoms together. So again, as soon as this guy moves away, these electrons move to here. This becomes slightly positive, which pulls on these electrons, and it satisfies its need because now it goes back to being neutral. But now this guy's positive, so it pulls on that guy's electrons, and this guy's now negative, so those negative electrons are going to pull towards another positive atom, so on and so forth. And so you just have the electrons basically being shared between every single, or pulled on, I should say, between every single atom within the metal. And the idea being that if I can get these electrons to move in one direction, I'm going to end up with electricity. So as they begin to flow, but it's the movement of electrons flowing is your current, and then the pressure that pushes them, the force that's driving them, is your voltage. Electron cloud can also transfer thermal energy, that is heat energy, which means that metals are not just good at conducting electricity, they're also very good at conducting heat. So now let's take a look at ionic bonding. We go to this animation, the ionic bonding tutorial, and now we're going to be filling in the blanks on our booklet handout. So here you've got, just a reminder, you're going to go to content, you're going to go to our chemistry unit, interactive animations, and click the ionic link here, and then afterwards we'll click the covalent link that's here as well. So here's the animation. So we're going to jump through looking at ionic bonding. This is an interactive animation, so in order to move through the slides, you're actually going to have to do what they say. When they say drag something closer, you drag it closer. So here we have two negatives. As we come closer, you can see that I can actually push the other negative away because like charges are going to repel, which is actually the very first thing we're going to talk about in our electricity unit. Okay. If I have opposite charges now and I bring the negative close, I'm actually going to see it attract. So I can pull this little positive around, or vice versa. The positive can attract the negative and pull it around. When they are close enough, they do stick together. And here we're going to see, you're on slide 4, but now on slide 5, as we're running through and looking at the slide, you're going to be using the information that's here to help you fill in our handout here. So opposite charges attract and stick together. Alike charges will repel each other. And in order to build an ionic compound, you have to have opposite charges. So you want to have a positive and a negative ion. So you've stolen electrons and you've given electrons to this guy. Because they're opposite, they will stick together. So positive ion is formed from an atom that has a tendency to lose electrons. Since metal can easily lose because they're less than half full, that positive ion will usually be a metal. And of course, this is where we find our metals on the left-hand side of the table. But remember, it's metals and poor little hydrogen up here on the top left-hand side. The negative ions then are the ones that tend to gain, again, because they're more than half full. And so you'll see that your nonmetals and some of your metalloids are going to be the ones that are going to end up gaining those electrons and forming a negative ion. Remember, we're not including the noble gases right over here on the right because, of course, they are both neutral and stable. They're not willing to form ions. So then we know that metals are going to form positive ions, or cations. Nonmetals are going to form negative ions, or anions. And that means that the metal that's positive and the nonmetal that is negative are able to bond together by forming an ionic bond. It's called an ionic bond because you have ions that are being attracted to one another. So we're going to take sodium and we're going to take chlorine from opposite sides of the table. Of course, this will be our metal and this will be our nonmetal. Remember that sodium is that soft metal we cut up in class and threw in the water and it burst into flame. Soft silvery metal belongs to the alkali metals. And here we have chlorine over here. This is the toxic mustard gas, yellow gas that would really do a number on your respiratory system. Very dangerous gas. But when we put them together as ions, you're going to find they're not so dangerous. They're more delicious than dangerous. Okay, so here we have our sodium and we have our chlorine. If we rip off an electron from the sodium, it becomes positively charged. The chlorine becomes negatively charged because it's got that extra. And its name is going to change from chlorine to chloride. And now you have a sodium ion and you have a chloride ion. Notice that we didn't bother to put the number 1 here and we didn't put the number 1 here. Usually the number 1 gets dropped off. If you had a 2 plus charge, you'd have to put the 2. But if you have a 1 plus charge, it's up to you whether you write 1 plus or whether you just show the plus sign. We're going to continue to write 1 plus because that'll make your senior level chemistry teacher very happy. But now the idea being that once they have opposite charges, they will attract and they will stick together. And that attraction between the two of them is called the ionic bond. It's not a very strong bond, but it's enough to hold them together for a while. Okay? Obviously, we're oversimplifying things, and this is more kind of what it would look like. Each chlorine atom needs one sodium to interact with. So here they're going to steal electrons. Now they become ions, and notice that they can stay together as little tiny units of one chlorine and one sodium. But here's what's going to end up happening if you had a lot of sodium and you had a lot of chlorine. It's not just going to be separate little molecules floating around. Instead, what's going to happen is you're going to see not just the opposite charges attracting between one sodium and one chlorine, but between all the sodiums and all the chlorines in the entire pile of things that you just mixed together. So the positive ions are going to attract the negative, just as negative will attract positive. And you'll end up with this kind of a thing. This is called an ionic crystal. If you have lots and lots and lots of them, they're going to automatically form like that, and they will become a nice little solid, and that solid is the ion crystal. Okay? Now, it's hard to tell, like, once they're in an ion crystal, is this sodium with this chlorine over here on the left, or is this sodium with this one to its right? You don't know, and it doesn't really matter which one it's actually connected to. In both cases, this is sodium chloride and this is sodium chloride. So instead of looking at exactly which atom is it, or I should say which ion is attached to which ion, this is going to end up telling us that we just need to know how many sodium ions we need for every chlorine. And you can see that it's a one-to-one relationship all the way along. For every sodium ion, there is one chlorine ion, and that's going to help us to determine our chemical formula. Okay, and keep in mind it's also in 3 dimensions, not just the 2 dimensions that you saw. So as you turn this, you can see that for every sodium there is a chloride ion. Remember that the name of the chlorine is going to change from an INE to an IDE ending. Okay, and again, you can flip that sucker around and play with it if you like. So in the 3D model, each ion is surrounded by oppositely charged ions. There are no distinct molecules. Instead of calling it a molecule then, what we actually call it is an ionic crystal. That's the real name for it. Because there's no single molecule within there, no distinct molecules. It's a compound. We've put together 2 different elements, so it is a compound, but we wouldn't call it a molecule. You have to call it an ionic crystal if it's an ionic bond. And here's how we would do the formula. So we take a look at another one. With this one, we're using sodium and chlorine again, but we're going to just quickly count them because they won't let us move through the animation without that. So we can see there is 3 sodium and 3 chlorine. But what you want to do when you're looking at the total amount here is you want to reduce the ratio. So 3 to 3 is the same thing as saying 1 to 1. So when you write the formula, you're going to say you need 1 sodium for every chlorine that you've got in that ionic crystal, NaCl. Notice again, we're not writing the little ones. There is 1 sodium ion for every 1 chlorine ion, but we don't bother to put the 1 because if we see sodium, we know there's 1 there. It's only if you would have 2 sodiums that you need to put a little 2 down below to say there's 2 of these, or if you had 2 chlorines, then you put a little 2 down below to say there's 2 of these guys. All right, so we're doing a ratio of the ions, not the total number. So let's go and run through a couple more. So here we've got this calcium and fluoride ions. All right, we can look to see how many there are. Looks to me like there are 4 gray guys. So 1, 2, 3, 4. And perhaps there are 1, 2, 3, 4 yellows there. And if I flip it on the bottom side, there's 4 yellows there. So it looks to me like there's 8. So then I say, well, it's for every 4, there's 8. So it's actually, if we reduce it, it's 1 to 2, right? So I know that there would be 1 calcium for every 2 fluoride ions. Click that sucker, move on. Okay, which is correct. So it's a 1 to 2 ratio because you're going to reduce the number. Because again, there's no molecules here. This is an ionic crystal. Who's attached to whom? We don't know. So we just do the ratio of the number of ions we're going to need. So again, we covered in this one how we got our ions. That's how when we strip electrons and we give them to other atoms. They stick together because they are oppositely charged. And we can write an ionic formula by looking at the ratio of how many cations you need for every anion that you've got. Quickly run over this again. Opposite charges attract to stick together. Alike charges repel each other. The positive ion is formed from an atom that has tendency to lose electrons. So those are metals plus little tiny hydrogen sitting over here. They can easily lose because their shells are less than half full. So they have 1, 2, or 3 electrons in their outside shell, more likely to lose. If it's a negative ion, it's formed from an atom that has a tendency to gain electrons. Nonmetals form ions by gaining electrons because their shells are more than half full. They have 4 or 5 or 6 or 7 electrons in their outside shell. Just have to top up their shells. Because they have opposite charges, metals and nonmetals can bond together, forming an ionic bond, a bond between ions. And this is how we're going to do our notation as we're moving forward. So really help you out for grade 10 as well. So here you can see we've got our sodium. In a neutral sodium atom, so we would call it a neutral atom, you have your regular core, you got your 11 and your 12 for your protons and your neutrons, and that comes from the atomic number is 11, so that's 11 protons. The entire mass would round up to 23. So if 11 of this 23 are protons, then it's 12 left over to be neutrons. Then we place our electrons, 2 in the first shell, 8 in the second shell. That's 10 there, but I have 11 electrons total in a neutral atom because they match the number of protons. So 1 spills out into the third shell. And of course, we do our Lewis dot diagram as well, where we have just the one dot that shows this one valence electron. Okay, chlorine, same thing, 17, 18 for our nucleus, and then 2, 8, 7 as we spread out our electrons in their shells. And then 7 is the valence, so we have 7 dots in the outside of this chlorine for our Lewis dot diagram. But when you go to make, let's say, the sodium over here, when this electron gets removed and you see it's been emptied out on the ion diagram for the Bohr-Rutherford, I've peeled down a layer down to this full shell. I can show that in my Lewis dot diagram by showing the fact that, look, there is no electron now in the original shell. And I do these big square brackets to show that I've made changes to that valence shell. And in fact, the change that I've made gets written right here on the outside to say, I've stolen that one electron that used to be here. It's gone. That's why there's no dots, because it's empty shell. And I now have a 1 plus charge. And this is how I show the Lewis dot diagram for this ion. Okay? It's going to be opposite, though, for chlorine, because chlorine had 7. It's almost full. It just needs 1 more. So when I fill it up, and I go, now I've got 2, 8, 18 of these electrons, instead of just 17 that I had before that matched. So I should have a 1 minus charge, because I have 1 extra electron than I had before. But I didn't strip down the layer like I did over here. In fact, I filled up all of those electrons. So I'm going to show the 8 dots that are in there to show that I have filled up the shell. How many did I have to add? I had to put in 1 extra electron than I had before. Okay, so that's how you're going to do these little ion versions of the Lewis dot diagrams. Now, the chlorine atom, we already showed this before, had a strong attraction for the electrons, and it was able to take one of those electrons from the sodium. So this electron on the original sodium will move to the chlorine. That's where it gets this 8 that it has to fill up the spot. And then this will become positively charged. This becomes negatively charged. And because they are oppositely charged, you're going to see them attract to one another. And then you're going to see the ionic crystal begin to form. Okay, so I needed one of these to satisfy one of these for the oppositely charged numbers. You're going to have enough of these and enough of these that when I put them together, it sums up to 0. Okay, remember that in chemical reactions, we don't do equal signs. We do arrows to show the direction that the reaction is running. So we have a sodium ion, and because chlorine is now an ion, we change its name from INE to IDE. So as soon as you put that little charge number there, it's called an oxidation number or a charge number, then as soon as you do that and you strip it of electrons or you give it electrons, all of the nonmetals are going to change to IDE. So this is actually a chloride ion, not a chlorine ion. Okay, so make sure you make this adjustment in your note as well. And this is exactly what we did when we ran through the animation. We counted them, 1, 2, 3 sodiums, 1, 2, 3 chlorines. That means the ratio is 1 to 1. So our formula, chemical formula for this ionic crystal for this compound is going to be sodium chloride in 1 to 1 ratio. In the ionic compounds, the formula again tells the ratio. We did this as well with the animation. Calcium ions, there's 4 of them. There was 8 fluoride. That's a 1 to 2 if I reduce the ratio. So the formula is 1 calcium ion to 2 fluoride ions. Right? So that is ionic bonding. When electrons get transferred from one atom to another, making ions, and then because they're oppositely charged, they attract to one another. The ions are formed when atoms achieve stable electron configuration. In other words, we were trying to give them full shells, either by peeling off electrons so we have a full shell below it like an onion, or by filling up and patching the gaps so we have a full shell like the chlorine ion that we saw earlier. Find the ratio that you'll need to form the compounds. So this is a very important little step that you're going to need to do. This will set you up for success in grade 10. So it's not just about testing this year, it's about getting you ready with the right information so you are a good grade 10 student as well. And here's what we do. We take our magnesium and our oxygen and we write out what it is that they're going to look like if they are neutral. So we would have 2 electrons for the magnesium, you'd have 6 electrons for the valence of the oxygen. And then I imagine what would happen if I made it an ion. If I strip off these 2 electrons, then I will have 2 positive charge because I am now 2 less negative than I was before. And if I fill up these 2 spots for electrons here on the oxygen, then I'm going to have a 2 minus or 2 negative charge because I'm going to add extra electrons here. These are now the ion forms. So this guy's name is now magnesium, and this guy's name is now oxide because it's no longer the neutral oxygen atom. Well, that makes our name very, very easy. It's now going to be called magnesium oxide. Notice that metals' names aren't going to change, but the non-metals, their names will change to the IDE ending. Okay, so what do I need? I got a 2 plus charge and a 2 minus charge. One of these is going to perfectly satisfy this guy's need for electrons. So it's a 1-to-1 ratio, which means that my chemical formula is 1 magnesium for every 1 oxygen ion. Okay. Then we look at calcium and chlorine, same idea. Draw their neutral version of their Lewis dot and strip off the electrons and make the ions. And notice I've ripped off 2, so it's a 2 plus charge. Here I'm going to have to add in 1 extra electron to satisfy chlorine, so it'll be a 1 minus charge. But why have I got this big 2 sitting here? Well, because if it's a 2 plus charge, I'm going to need a couple of these chlorine with the 1 minus. I need 2 of these guys to satisfy this. And in chemistry notation, when you're saying you have 2 of something, you would put this huge big number out in front. It's called a coefficient, and you would say there's 2 of these required for every one of these. But when you actually put it into the formula and you're counting ions, you're going to say I need 1 of these for every 2 of the chlorines, and it goes to being a subscript when it becomes an actual neutral compound. Remember, not a molecule, but an ionic crystal. Okay, so you're going to run through and you're going to do the practice here. You're going to do this on your own first, please, before you copy any of this. See what you can do. Then you come back and you can check the answer keys and you can run through. So pause this right now, give this a shot on your own, and then come back and I'll walk you through it real quick. So here we have our potassium, 1 electron in the outside shell, it becomes a 1 plus charge. 1 missing in fluorine's outside shell, so it becomes a 1 minus. It's a 1-to-1 relationship. And again, potassium fluoride, because I'm going to change the fluorine name to IDE. Then you get magnesium and iodine, 2 electrons, so I get the 2 plus charge, a 1 missing, so it's a 1 minus charge. Because it's a 2 plus and a 1 minus, I'm going to need 2 of these guys in order to satisfy it. So MgI2, and magnesium iodide is its fancy name, because the iodine, Ne becomes De when it becomes an ion. Then you see here with the sodium, it'll be a 1 plus charge because I got 1 electron to lose. There's 2 spaces for electrons, so it'll be a 2 negative. But now notice that we've reversed the charges here. So we've got a 1 plus and a 2 minus. I'm going to need 2 of these so that I have an overall 2 plus charge so that I can satisfy that. So I'll need Na2O. And again, sodium oxide, because this is an oxide ion as soon as the oxygen gains electrons. Aluminum has 3. Chlorine has 7, so it'll be 3 plus and a 1 minus, just like the others. And because it's a 1 minus, I'm actually going to need 3 of these guys. So 3 times the 1 gives me 3 negative to satisfy this 3 positive, because I want them to add up to 0. And so I'll need AlCl3, and I'll have aluminum chloride. And again, it's really important that you notice that the metals form ions. And when they do that, they do not change their names. So it was aluminum it wasn't a lumide or something silly. It was just the metals keep their names. It's only the non-metals that change to the IDE. Okay. Some of these changes are a little bit tricky. So sulfur will change to sulfide. Phosphorus changes to phosphide. Oxygen changes to oxide. Nitrogen changes to nitride. The other ones are pretty straightforward. So please go through and work through this so that you can understand how to do the actual naming. Check your answers before moving on to the next part of this lesson. So pause here, try these, check your answers, come back and finish this video at this point. So we've covered ionic bonding now, and now we're going to run through covalent bonding. Remember that co is that word we talked about where we're saying we're sharing. What are we sharing? We're sharing the valence electrons. Not all the electrons, just the ones in the outside shell. Okay? When the electrons are held tightly by their atoms, in other words, they're more than half full, they do not give up their electrons. In order to become stable, if they're not going to give electrons away and they want to become stable and fill up their shell, then they're going to have to share electrons. That's the only way. If they're not able to steal them from a metal, then these non-metals, which is what we're dealing with here, they're going to have to just share custody of those electrons. And so they will have a full outer shell most of the time. The electrons will spend some time around the one atom and some time around the other. So to complete this section, I'd like you to go to the covalent bonding slides, which you can find by going again to our class page. You're going to look under Chemistry Unit, Interactive Animations, and click here for the covalent bonding slides. Okay, so covalent bonding, typically explained as a bond that forms when atoms are sharing electrons. It's not 100% true that they're sharing, but you'll see that for yourself in a moment. In this tutorial, we'll explore what this means and how the process of sharing electrons can hold two atoms together. So how can they be stuck together if they're sharing electrons? Okay, so we have to figure out how they actually work. I'm going to take these two atoms, we're going to move them around. So the box below, we have two hydrogen atoms, move them around to see how they interact. So if I move this atom a little bit closer, and you see the big thing is the proton and the little black thing is the electron, you can see that the behavior of the electrons, whoop, there we go, they suddenly start to become attracted to one another's nucleus. So the electron from this guy that's floating around suddenly becomes attracted to this proton over here and vice versa. This electron, it's moving so quickly it looks like more than one, but there is just one. It's going to be attracted to this nucleus as we move through. You can see that begin to happen. See the electrons begin to become in between those guys, and this is what we mean by sharing. And if we get close enough, we can actually cause the bond to happen, because the one electron will always be attracted to the other guy's nucleus and vice versa. Okay, so stick them together and you actually form a nice little bond, and you can drag them around together and they'll stay stuck. This is a much stronger bond because they're sharing than the ionic crystals that we saw before. The crystals are very easy to break apart because they're not really molecules, whereas this is now a molecule. It's an H2 molecule. Okay, so how is the movement different? What happens if you try to move them closer together? Well, we see that we have this little attraction going on when we put them together. So a couple ways to kind of look at what's going on here. So we have a line now that shows who's attracted to, or sorry, I should say who's attached to whom. And so the atom on the right loves its own electron, and the atom on the left loves its own electron, but we haven't bothered to show the line on the right. So here's what's going to happen. This guy hangs onto its own electron. You see that its electron now gets pulled towards the other guy, and so this guy's electron also gets pulled. And now you've got the tug. This guy wants both of the electrons because that would fill up its outer shell. Remember that it only needs two to be full if it's hydrogen. It only has one shell. But this guy also wants both of those electrons. So it's a little less of a sharing and more of a tug-of-war between the electrons that are attracting both of those nuclei. And so because they're both pulling on the same electrons, they are going to want to pull together. So it's a covalent bond. Again, the atoms are not really sharing electrons as much as they are fighting over them. They are both trying to attract the same electrons, but neither one can actually take them away from the other. This creates a situation in which both atoms are pulled together. Which atoms would be doing this? Well, not the metals over here. These guys form cations. They're not going to be sharing electrons, but these guys right here will be. The non-metals are going to, because they're more than half full, they have a strong hold on their electrons. Nobody's going to be able to steal them from them, but they're willing to at least try to steal each other's, and they'll do that, and it looks like they're sharing. That's why we call it a covalent bond. Okay, covalent bond between two non-metal atoms. That's an important point. You would never get a covalent bond between metals, and you would never get a covalent bond between metals and nonmetals. It's only formed between the nonmetal with another nonmetal. Remember again that poor little hydrogen over here, abandoned on the left-hand side, is a nonmetal, and it can form covalent bonds with other nonmetals. Even though it can also form a cation, it will form a covalent bond. All right, and that's the end of using this animation because it gets into some more complicated things that we don't really need to discuss. So we're going to skip from 13. We're going to head back to our note to fill in the blanks. So here we have the covalent bond forms when atoms are sharing. And again, the number 1 here tells you which slide we stole this off of. Number 3 tells us we got it from slide 3, or at least the concept of it. Now we're writing our own answer. We were just answering the questions that were on slide 3. So what is the question? How is the movement of electrons different when the atoms are close? Well, the electrons of one atom are going to get attracted to the nucleus of the other atom. That's what we saw. What happens if you try to move the atoms very close together? They form a chemical bond by sharing the electrons in between them. When the two atoms are close enough, the nucleus of one atom begins to weakly attract the other one. Remember, we moved this guy in, and then this electron suddenly started to want to be near this guy over here. When the atoms get even closer, the nucleus of one atom has a strong attraction for its own electron and the electron from the other guy. So we have this guy pulling on this one and this guy pulling on the other guys as well. And so the electrons actually end up hanging out in between the two nuclei most of the time there. And again, this is the covalent bond. This is called a shared pair of electrons. The atoms are not really sharing again. They're fighting over them. Neither one can take the electrons away, so both are pulled together. And again, that happens in the non-metal area. For just nonmetals with nonmetals, not metals with metals, that would be a metallic bond. Not metals with nonmetals, that would be an ionic bond. But nonmetals with nonmetals is a covalent bond. Okay. Now you're going to jump back to the interactive and you're going to look at the slides 25 to 35. So let's go there now. All right, so here we are on slide 25, and what we're going to be doing is figuring out how we name these very simple covalent compounds. So here's our problem. This one is nitrogen with oxygen, but this one is nitrogen with oxygen. So we can't just call this nitrogen oxide and then O2, because what would we call this guy? This one is nitrogen oxide as well, but it has a different number. And I can't just tell you, go get the nitrogen oxide from the cupboard, because you'd say, well, which one do you want me to go and get? Do you want the NO2 version or do you want the N2O3 version? So instead what we're going to have to do is count the number of atoms in this molecule. So we call it nitrogen dioxide because there are 2 of the oxides. Then here we've got 2 nitrogens with 3 oxygens, so it's dinitrogen, so 2 nitrogens, trioxide. Carbon, 1 to 4, so it's carbon tetra. Tetra is the Greek prefix for 4. So 1 carbon and 4 chlorides. 2 chlorines, 1, so we have a monoxide. And then disulfur dichloride here. Notice that when we only had 1 nitrogen for the first element, we didn't worry about the mono. That's just a little short form trick that they say, don't worry about if there's only 1 of the first, just say its name. But if there's only 1 of the second, like down here with the chlorine and the oxygen, then we have to mention that there's only 1 of them. Also notice that the whole word is mono, but because it's mono with the oxide, we don't want to say mono with 2 O's in the middle. It'll be very awkward. Monoxide is just a weird thing to say. So they just drop off the letter there and they say monoxide. Okay, so we notice again as well, we have the IDE endings, not just the different numbers, but the IDEs. And again, those prefixes tell us how many each of the atoms are in these molecules. Okay, mono, di, tri, tetra, penta, hexa. This is written on your note for you. You just need to know 1, 2, 3, 4, 5, 6 is what they actually mean. And again, no mono if it's the first one, it's only mono if it is the second one. So what do you want to call this one? N2O. You're going to run through this animation, you're going to grab your answers and drag them over. The animation is not going to let you go to the next slide until you've got the right answers. So now that you've seen a covalent bond, the sharing of electrons, covalent bonds are going to form molecular compounds or covalent compounds. They actually form molecules as opposed to ionic crystals. Okay? And again, it's with nonmetals, and you're going to share the electrons with those covalent bonds. So the covalent bonds, again, two atoms each contribute one electron to form a pair. That pair of electrons between them that they're fighting over, that's their chemical bond, is what holds them together. So here we had, again, in our animation, we had the little hydrogens and we had the electrons being attracted in between. This guy attracted to this guy attracted to this guy's core. And then with our Lewis dot diagram, what we would show is those two electrons, we would show them being in between them, and that is what we would call the Lewis dot diagram. But we don't like to draw dots if we don't have to. So what they've done is they've taken the idea of anything that's shared, and you remove the two electrons and you show a line instead. And that line represents the shared pair of electrons, or what we call the bond. Once you do that and you replace the shared pair with the line, you now have what we call a Lewis structure. So here's some examples as we run through. If we're given this little molecule here, CH4, which is called methane, then we can quickly draw our carbon, Lewis dot, and our hydrogen, and we see that the carbon actually has 4 spots where hydrogen electrons can go. And that's why you end up seeing carbon with 4 of these hydrogens. So we're going to say carbon's the one with all the spots, so it must be the central one. We pop in all of our hydrogens, but we don't want to leave these dots here, so instead we replace the shared dots. So there's 2, 2, 2, 2. Notice that carbon now has 8 around it, so it's happy. And the hydrogen now has 2 around it. Remember, it only needs 2 to be happy. So every hydrogen is also satisfied. So they're going to stick together nice and tight. And when we take these double pair of electrons and we change the symbol to the line. So this would be the Lewis structure for this particular combination. So this, in all cases, this is methane, but this is the nicer way to draw it. Okay? Ammonia, NH3. You might want to start memorizing these names, by the way, to be useful for grade 10. Methane being CH4, ammonia being NH3. We draw it and we see, oh, look, there's 1, 2, 3 spaces for electrons. This one just has place for 1. So when I draw my nitrogen, this space is already filled up. So I put hydrogen, hydrogen, hydrogen. That's why it ends up being NH3. And then I replace the shared electrons with the lines. But notice that these electrons here at the top did not get shared. They belong only to the nitrogen. So we show that they belong here down in the green only to the nitrogen. You always need to make sure that you don't just draw the lines for the shared pairs, but you also draw the unshared pairs of electrons as well. Here we have oxygen. Notice that it's a couple oxygens attached to each other. So it's going to have the 6 and it has 6. The 2 in between get attracted. These guys get attracted to one another. And because it only has as the same type of atom to satisfy itself, we end up with 2 shared pairs in between them, because they need to share all of those. And so we don't just draw one line, we actually draw what's called a double bond. So over here we had single bonds because there's only one pair, and now we've got double bonds shared between them. And we have to still show the unshared pairs of electrons when we draw our diagrams. So you're going to run through and you're going to take a look at drawing these, and then you can always come back. So pause this lesson, see what you can do with it, and then come back and take a look at my explanations as we run through. So here we have hydrogen peroxide. This is another good one for you to memorize, H2O2. So I've got my oxygen in the red, oxygen in the purple. They both have 6. There's a shared pair between them. There's a shared pair between the hydrogens, and away we go. So we get rid of the shared pairs, and we show them as bonds, but we have to make sure that we keep the unshared pairs still written in our diagram. Carbon dioxide. So I've got 1 carbon with 2 oxygens. That carbon's going to go in the center, because it's the one that needs the most. So you're going to have these 2 and these 2 being shared between these 2. This one here and then this pair over here are going to get shared. So that ends up with 2 in the middle here, 2 in the middle there. I must have a double bond, as you can see in the green. And I have to show the unshared pairs that are on the edge get showed along here as well. Okay. Carbon tetrabromide. So I know carbon is, there must be 1 of these, there must be 4 of the bromines. Carbon's going to go in the center, and the bromines are going to attach this way. Bromine only needs 1 electron. Carbon needs 4, so that's why you're going to end up with 4 around there like that. With the shared pairs, I'm going to replace that with a line. Don't forget to show the ones that were not shared, and you show them around the outside of those little atoms there, okay? So this is our tetrabromide, carbon tetrabromide. Here we have hydrogen chloride, 1 to 1. So we have 1 of these, simple 1 line. Don't forget to show the unshared pairs. Hydrogen sulfide. Again, this guy's got 6. These ones each have 1. So I've just lined up my electrons to make it easy. This is going to be the shared pair. This is going to be the shared pair. So line, line, don't forget the unshared pairs. And here a little bit trickier, we've got a couple carbons and a hydrogen. So we have one joining in between here, and then we have space for 1, 2, 3, 4, 5, 6. That's what it told us. So we spread them out along the outside of the carbons, and we end up with this molecule right here. There are no unshared pairs. That's why you don't see any extra dots anywhere. Phosphorus trichloride. We've got our 1 phosphorus and 3 of these guys. So 1 phosphorus, 3 of these guys wrapped around. So we got 5 dots or 5 electrons for phosphorus, 7 for each of the chlorines. And then again, there's our shared pair, shared pair, shared pair. Show it with a line. Don't forget all the unshared pairs must be drawn around the diagram. In class, you're going to have a molecule kit, and you're going to be able to build these suckers. And what you're going to be doing after you build them, you're going to see that there's only 1 space on each of the hydrogens. There's only 2 spaces on the oxygen, and there's 4 on the carbon and 3. And that's just based on, if you go back up here, the carbon had 4 spots, the hydrogen only had 1. Sulfur would have had 2 spots, so it would have had 2 holes, just like oxygen would have 2 holes, etc.
We can see from the key that the white piece with 1 hole represents hydrogen. The black piece with 4 holes represents carbon. The short and rigid piece represents a single bond. The long and flexible piece represents a double bond. Let's build ethylene, which has the formula C2H4. Ethylene has a double bond between the carbons and single bonds between each hydrogen and carbon. To create a double bond, gather 2 of the long flexible pieces and use them to connect the carbon atoms together. Then create the 4 single bonds using the short rigid pieces to connect the hydrogen and carbon atoms together. Congratulations! You've built your first molecule.
So then you're going to build those little molecules, and then you're going to draw out how they stuck together. And you're going to see that the hydrogen stuck to the oxygen, and then the other hydrogen also stuck to the oxygen. And when you come to draw your Lewis structure, just don't forget the unshared pairs. When you do the nitrogen gas, you're going to find that you actually, because there's only nitrogen and nitrogen joining together, you would have had for all 3 holes that are available in the nitrogen and all 3 that are here, they just connect to each other, forming a triple bond. Then the ethene would have been the carbon. You would have shoved them together, and you would have seen that there are just enough space to put in the 4 hydrogens. So there would have been double bond to join those. And with the acetylene, which is a really fun thing you're going to produce in grade 10 for a lab, a nice little explosive lab in grade 10, you're going to have 3 spaces on the carbons, and only one of them, or I should say you have 4 spaces on the carbons total, but only one of those 4 spaces gets satisfied with a hydrogen, so the carbons have to help each other out, and all of the other 3 will join between those carbons. Okay? Next thing I'd like you to do is run through and practice naming, then you can check your answers, and that is the end of our lesson.